Hello and welcome. Today we are going to study a new topic, which is digital frequency meters. So far we have seen in this part we have broadly reviewed starting from flip-flops up to counters on one side, that is from the digital electronic side, and on the other side from the analog electronics we have reviewed about the op-amp. So I thought, why do we not start putting these things into use and make some nice measuring instruments, which is the goal of this course. So today we are going to use counters, basically counters from digital electronics, and make digital frequency meters out of it. Okay. So first thing that we will look at is how to measure frequency of a square wave, square or rectangular wave. Okay. So the signal is like this. Okay. It can be square, that means the positives, the width of this part positive half and the width of the negative half may be equal or may not be equal, that means rectangular wave. Okay. So this is the input signal, and the question is we have how to measure the frequency of this signal. What is frequency? Frequency is nothing but the number of cycles, complete cycles per unit time, right? So that is equivalent to, say, number of this positive edges or this negative edges that occur per unit time. Say for example, if we count the number of this negative edges per second, that will give us the frequency, right? So frequency is nothing but the number of falling edges divided by time, per unit time. So basically what we have to do is measure the or count the number of these edges within a given amount of time. Okay, how do we do that? So let's take a counter. So let this be a counter with a number of flip-flops in it. So each small cell here will represent one flip-flop. Okay, so that means this is a 4-bit counter. So if you recall very quickly, so a counter is a set of T flip-flops, ripple counter, and you know that the output of one flip-flop goes to the clock of the next flip-flop. So this is Q, this is the enable of the next flip-flop, and this is a edge triggered flip-flop. This is more precisely a negative edge triggered flip-flop. Similarly, from here the output goes there, and from here the output goes there. So this we have studied in length. Okay, and here the first one will get the signal from outside, because all other flip-flops are getting their clocks from the previous output or the output of the previous T flip-flop, but here there is no previous one. Okay, this is the first one. So therefore it will get the input from a clock generator or some source of a square wave or something. Okay, so this set of 4 T flip-flops, so these are T flip-flops, all these T's are, you know, at logic level 1, these are enables. So this is what we have studied before, and this is the input. And now I'm drawing this counter symbolically like this. So these 4 cells, 4 boxes are 4 bits or 4 flip-flops inside. Okay. Then okay, so let me draw the input here. This input is this input. Okay, and what else? Now how to use this counter to measure this frequency? Okay, answer is simple. Simply give or apply this input signal here. Okay, you just apply this input signal here. So how do you have? We have this square wave here, square or rectangular wave here, and that means this negative edges are coming at the input, and this, let me take this as a negative edge triggered counter. So this is a counter. Okay, particularly this is a 4-bit counter. You can take more number of bits if required. So then what will happen? As this negative edges come here one by one, okay, then this count here will increase continuously. So starting from the value of 0, 0, 0, 0, then when this next negative edge comes, it will become 0, 0, 0, 1. After that, when this one comes at this point, this will become 1, 0. Then at this instant here, it will become 1, 1, and so on. This way counting will progress, right? Now I have to make sure that, so I have to make sure that the counting starts from 0 and the counting is stopped after a pre-specified time, maybe 1 second. Example, 1 second. Then what will happen? So the counting starts from the value 0 and the counting continues for 1 second. That means after 1 second, whatever will be the value of this counter, okay, whatever is there in whatever is the value after 1 second, that will directly give me the frequency of this input signal, right? Similarly, okay, if this counting time, pre-specified, preset, predetermined counting time is say 100 millisecond instead of 1 second, if it is 100 millisecond. So let's take an example. So if counting time, which is often called as gate time, okay, if the counting time or gate time is equal to say 100 millisecond, and if the counter value is say 15 after this 100 millisecond, starting from the value of 0, then what is the frequency? It's very simple. It's nothing but, so frequency is nothing but the count of this negative edges divided by the time. Time is 100 millisecond. So this is nothing but 15 by this is 0.1 second, 0.1 second. So this will become 150 hertz, 150 per second. That's 150 hertz, as simple as that. And the logic is very simple. So if I have just a counter, I can give this square wave at the input, making sure that the counting starts with the value of 0 and I stop the counting after a pre-specified time. Then this way I can find the frequency, very simple. Okay. Now these are the two important things that you have to make sure, that counting should start from 0 and that it is stopped, counting is stopped after some time. These are the two important things. Now how do we do that? To do that, we will need a reset input of this counter. Okay. So we will use a reset input of the counter to start the counting from 0. Okay. So the counter will have at least two inputs. One is what we have already seen, this one. Let's call this the clock. Okay. And it should have another input other than the clock. So if this is clock, we need another input, reset, and this can also be a edge triggered input. Okay. So that the function of this reset is, as soon as you give a edge, all the bits, that means all the flip flops, will reset to 0 immediately. Okay. So function of reset is to make all bits equal to 0 as soon as a positive edge or rising edge, okay, as soon as a rising edge comes at reset. Okay. Now how is this implemented internally? That means how is this reset input connected to this T flip flops? That's a different question. Or how are these T flip flops made so that this reset input can be realized? That's a different question. Okay, that's also an interesting question, but we are not going into that much detail. If you are interested, please try it yourself and you can share your idea in the forum with us. We are now looking at it from an external or superficial perspective, functional perspective. We are just saying that this counter will have a input which we will call the reset, and as soon as you give this rising edge, okay, all the bits will become 0 immediately. So this is the function of reset, and this is the symbol. So this symbol triangle, indicates a edge triggered input. I could also put a bubble here if I need a negative edge triggered input. I can use that. Okay. So how to use this reset? Make sure that before you start counting, okay, so that means at the moment t equal to 0, time equal to 0, before applying this input here, give a rising edge here somehow, so that all the bits are set to 0, and then let the inputs come here. Okay. So this is one thing that we need. Now the other thing that we have to make sure that the counting is stopped after 1 second or some time. How do we realize that? So for that we can do this. So let this be the counter. Okay. So we have two inputs. This is the clock and this is reset. Now what I can do, instead of applying the input directly here, I will first connect an AND gate, a 2 input AND gate, and here I will give the input, which is this square wave, right, and here the other one I will use to switch on and off the counting. Okay. So call this some G, call this input G. Okay. So what we have to do is this: make sure that G is equal to high or logical 1 within the counting time and G is equal to low or logical 0 after the counting or get time. Okay. So this is the counter. So let me just state everything once again. So what we have to do, say if this is my time, this is time axis, and the input signal is like this, it's a square wave. Like this, and so what I have to do, so this is t equal to 0. Okay. So at t equal to 0, give a rising edge at reset. That means reset all the values to 0, all the flip bits to 0. Okay. And then starting from here to say this is 1 second, say this is t equal to 1 second or the pre-specified counting time, this can be 100 millisecond, 10 millisecond, 2 second, 10 second, whatever you choose as the counting time. So then what we have to do? So we have to make sure that G is 1 from here to here, and then here it should be 0. Okay. So let me draw G. This is t equal to 0. So starting from here up to this point, G should be 1. So this is G gate signal, and then here it should be 0. If we do not make it 0 here, then what will happen? The counter will continue to count, and the count will keep increasing, right? So, but we want to measure only the number of edges in 1 second. So after 1 second or the pre-specified time, we have to stop it. Okay. So this is the fundamental idea of a frequency meter. Okay, so if you have understood up to this, that's really great. And in the next video, we will talk in the next class we will talk about more and more details. Okay, and see how much we can go on. Thank you.